Good day, class. For this video, we're going to talk about the volume of revolution, or in some references, volume of rotation of functions about the x and y axis. This video will focus on one of the methods, the disk method, which in calculus terms makes use of infinitesimally thin disks that make up the entire volume spanned by the rotation. In this lesson, we will learn a few things. First, I'm going to give you some intuition of how mathematicians have come up with the idea of the disk method. Next, from this intuition, we will derive the actual formula in finding the volume. There's actually one formula, but it varies just a little bit depending upon the axis where this function revolves about. Finally, we will apply this formula in various examples that I will present later on. I will assume that you have some background on definite integration in calculus, so we could focus more on how we've come up with the disk method formula. If you love geometry, you may remember the formula that we use in finding the volume of the cylinder: pi multiplied by the radius squared multiplied by the height. Why would anyone forget that anyway? Imagine the same cylinder, but with the height infinitesimally small that most people refer to it as a disk, shaped like a CD or a coin. Now I'm going to show you an awkwardly looking cylinder which somewhat reminds me of the Leaning Tower of Pisa. I wonder, how do we compute for the volume of shapes like these? The theory here is that we can make use of the disks we've seen earlier, where we have a known formula for its volume. Stack them up together to form an approximately similar shape, and voila, we approximate the volume of something that looks like this. Or maybe not just a cylinder. Perhaps as long as when you look directly from the top, it somehow still appears to be a circle and can be represented by a disk. This leads us to the disk method in finding the volume of revolution. I'm going to demonstrate a rotation of some two-dimensional function y is equal to the square root of x between the values x equals 0 and x equals 3. I rotate it about the x-axis. The volume spanned by the rotation looks like this. As you see, we can estimate the volume of this figure using an infinite number of cylinders. From this point, you may be thinking, do we need to compute every single volume of each cylinder we use to approximate the figure's volume? Not actually. The beauty of calculus is that infinity doesn't limit someone from obtaining a pretty close approximation, and this turns out to be one of the applications of integration, apart from finding the area between curves, of course. Let's derive the formula. Again, the process is that we add up the volume of these infinite cylinders, or in calculus terms, integrate the volume that we get from each cylinder. We are usually bound by some limit here, as we can't practically find the volume of something infinite rotated toward an axis. As for instance, the formula I've shown earlier, where I've set the limits from x equals 0 to x equals 3. This means that I only need to find the volume between these values so I can obtain a finite answer. Take note that the lower value a is at the bottom, and the higher value b is at the top. Now what is the formula for the volume of a cylinder again? It's pi multiplied by the radius squared multiplied by the height. The total height of the cylinders is represented by the limits mentioned earlier. So two things remain, the pi and the radius squared. We have a theorem in calculus that the integral of a constant multiplied to a function is the constant multiplied to the integral of a function. So we can put this one outside the integral. Now, how about the radius? If we look back to the earlier graph closely, the radius of these cylinders vary as a function itself. So basically, we substitute the value of, in this case, y to the radius, which we will refer to as a function r of x squared for the meantime. The final formula would be v is equal to pi multiplied by the integral of r of x squared dx from a to b. Now we have come up with what we need to solve for the volume of a function revolving around the x-axis. Let's try some examples. Let's look back at the first function we've seen. Y is equal to the square root of x between the values x equals 0 and x equals 3. Using the formula we derived, we're going to find the volume of this figure created after rotating the function about the x-axis. The formula is, again, this one. V is equal to pi multiplied by the integral of r of x squared dx from a to b. We know that the volume we will compute is from x equals 0 to x equals 3. So we substitute those values for a and b respectively. Now, How about the function r of x squared? Let's look at this graph. If we take a certain x value within the range and find the radius when it is rotated, it appears to be equal to the corresponding y value itself. So it's not a surprise. The function of r of x squared is a function y squared. In this example, y equals the square root of x, so we will substitute square root of x inside the parenthesis. The radical and the exponent cancel each other out, so we have a linear expression. V equals pi multiplied to the integral of x dx from 0 to 3. Now it gets pretty straightforward from here. We evaluate the definite integral of the expression from 0 to 3, and we have the final answer of 9/2 pi units cubed. Usually, we don't need to specify the units since we all know we're talking about volume in a 3-dimensional coordinate system. But I've included it here in the first example for clarity. Let's try another example. Consider the function y equals 1 over x, where it rotates about the x-axis. Let's calculate the volume of rotation from x equals 1 to x equals 3. Now you may be wondering, how about the part of the curve in the third quadrant? It's not within the range specified, so what are we going to do with it? Good question. In fact, we only should be considering the curve in the first quadrant. So let's just omit the rest for cleaner graph. After rotation, we see a figure that looks like a horn or the big edge of a trumpet. Now let's compute for the volume of this figure. Again, we use the formula V is equal to y multiplied by the integral of r of x squared dx from a to b. Replace a with 1, b with 3, and the function r of x with 1 over x. Then integrate as shown here. And there you have the final answer, 2/3 pi. So what if the figure is instead rotated about the y-axis? As I've said earlier, there is only one formula, but we will be tweaking some variables here. The takeaway is that the concept of thin disks approximating the volume is the same. Since the rotation is about the vertical axis, we will be setting the limits from a vertical perspective as well. Arbitrarily, we will be defining the integral from c to d in the y-axis. The function and the integral itself is now also in terms of y. So we will use r of y squared dy instead. Here is the final formula. V is equal to pi multiplied by the integral of r of y squared dy from c to d. Let's try some examples using this formula. This parabola represented by the function y equals x squared is rotated about the y-axis. From the y-axis itself to y equals 4, compute the volume of this figure produced by the rotation. Using the formula V is equal to pi multiplied by the integral of r of y squared dy from c to d, substitute the values 0 and 4 as the limits c and d respectively. Now, there's a catch here. Since the rotation is vertical, the radius represented is now horizontal. If we take for instance a y value within the range, the respective radius is represented by the corresponding x value. So in order to get r of y, we must convert the entire expression into something equated to x. We will convert y equals x squared into a new expression. To remove the exponent on the x variable, we will add a radical to both sides of the equation. Now we have a new function equated to x. X equals the square root of y. We can finally plug this one into the formula. V is equal to pi multiplied by the integral of square root of y squared dy from 0 to 4. Simplify the formula like in the previous examples. And then we go into the usual definite integration process. There we have the answer, 8 pi. Let's try another example. Consider y equals x raised to 2/3, bounded by x equals 0, and rotated about the y-axis. As you see, this one looks like a funnel when rotated. Let's find the volume of the figure from the y-axis to y equals 1. Going back to the formula, we substitute 0 for c and 1 for d, and then we must convert the y equals x raised to 2/3 in terms of y. Raise both sides of the equation to 3/2. From the loss of exponents, we know that these two exponents cancel out, and the new expression we get is x equals y raised to 3/2. This will be our new r of y. Raising it to the power of 2 cancels out the denominator of the function's exponent, and now we simply have the equation v is equal to pi multiplied by the integral of y cubed
dy
from 0 to 1. And here are the preceding steps of the definite integration. Finally, we have the answer 1/4 pi. So that concludes our topic in volume of rotation about the x and y axis using the disk method. We've been enlightened by the intuition that we can fairly estimate the volume of such figures with an infinite number of thin disks. Hopefully you understood the concepts behind the procedure, and I hope you liked the video as well.